All right, so today we're taking a look at implicit differentiation. For those of you who are watching this later, we are taking a look at what this even means. So far, in terms of what we understand, we know what it means to differentiate a function, to take the derivative. But what we haven't really studied is this implicit part. So we're going to back up a step and talk about, well, what is an implicit function versus, we don't really call them explicit functions, but what is the contrast there? So when we say a function, normally we're used to solving for y, writing y equals, so that we can replace that y with f of x and write in function notation. So for example, x squared minus 4. We might even say this is a explicit function. It has y as a function of x, versus the first one we're going to take a look at in our upcoming example, something like x squared plus y squared equals 16. Now, in this particular example, hopefully we recognize this shape. This is a circle, remember from pre-calc. And this circle has a radius of 4, and it's centered at the origin. Now, if you don't remember that, that's okay. We would just drop this into Desmos, create a graph, take a look at it. A lot of the implicit functions we see, this one is implicit, then we're going to not necessarily recognize the shape. It's going to be kind of rare that we say, aha, I know what that is. Most of them we look at, I might not know what it is unless I stick it in Desmos. So let's think about the difference between the two. For a function, we know a function has to pass the vertical line test. So this guy does. Whereas if we think about our circle, we have multiple places where we fail the vertical line test. So in general, our implicit functions are going to create some issues, potentially, if we solve for y. Think about what happens in our circle case. If we tried to solve for y, we could write y squared equals negative x squared plus 16. Then we could think about taking the square root. But when we go from y squared to y, we would actually have to take the positive and negative square root. What this actually does is creates the top half and the bottom half of our circle, so that if you just look at the positive square root, you're looking at a function. And if you just look at the negative square root, you're looking at a function. So things that are functions, we've learned how to differentiate. We have the tools to differentiate almost any function we want to at this point, if we can do the rules correctly. But what we don't know how to do is differentiate implicit functions, where it's either not a function because it fails the vertical line test, or maybe it's difficult to solve for y. So let me give you another example. Let's just squeeze it down here. Let's say we'll look at this one later as well. X squared plus y cubed equals y. So right now, we probably don't have the tools we need to solve for y, but notice there's y's on both sides of the equation. There's a higher power that's going to make it difficult to isolate that y. And even if we can do it, it's potentially going to be a little bit messy. So what we do with implicit differentiation is look at an alternate technique. The technique actually works for functions or explicit functions, but we don't necessarily need it. So let's take a look at our process in this case. What we're going to do with implicit differentiation, our key steps, we're going to think about both sides of the equation separately. Because we don't just have y equals on one side and then something involving x on the other, we're going to think about two pieces. And what we're going to do is differentiate both sides. So in essence, it's going to become kind of a double problem for us. And we're going to be careful that we're going to differentiate with respect to, we'll say that a whole lot today, with respect to a particular variable. Most of the time we're going to use an x, but we can change that up if we need to. Okay. What's our goal? Even if we understand the idea we're going to differentiate both sides, we're going to try to find dy dx. So the goal is still to find the derivative, and it's the derivative of our y's with respect to x. Think about this as still dy dx is representing our instantaneous slope. All of this is a little bit abstract. Let's go through our first example, and then I'll give you guys a couple minutes to ask questions. let's go ahead and return back to the circle. If you guys hear that, what sounds like thunder upstairs, that's my other little kid. He's 4, running around, making lots of noise up there. I don't know how much it'll come through on Zoom here. So when we take a look at this equation, let me just use some colors here, some brackets. Got left side and right side. And what we're going to do is differentiate both sides with respect to x. So when we differentiate with respect to x, I like to use the operator notation. And let's just focus on the right side for a second. So if I just cover up the left side, in fact, I'm just going to erase it. And I said, focus on what is the derivative of 16 with respect to x. Well, 16 is a constant. The derivative of 16 with respect to x is 0. So we've got that piece, but what we're actually doing is we've only done one side. So let's put our other side back. And this is the trickier side. We're going to differentiate with respect to x. Now, if I just had the derivative and I just had an x squared, we know how to differentiate the x squared with respect to x, no problem. It's really when we have our y's that we start to see some problems. First step here, though, you want to remember the derivative rules that you can use to break it down as much as you can and handle it piece by piece. The more you can separate things out, the better. Some cases we can do it easily, other cases it gets more difficult. So let's take a look, change this back here, to splitting it up. We can split up our derivatives with addition, so the derivative of x squared with respect to x, and then the derivative of y squared with respect to x. We just carry down the equal 0 and focus on our first component. We know the derivative of x squared with respect to x is going to be 2x. Then if we think about the derivative of y squared with respect to x, that's something that we've talked about a little bit with chain rule, but it feels strange to us. We talked about take the derivative of the outer with respect to the inner and follow it by the derivative of the inner, kind of summing up chain rule. And we talked about du dx and dy dx as being different. And we talked about differentiating with respect to kind of an inner function and the outer function. But in this case, I want you to pretend for a minute that instead of x, we substituted a y, the derivative of y squared with respect to y. What that's saying is we're differentiating y squared and y is the variable. Whereas when we say the derivative of y squared with respect to x, we're looking at y squared, but our variable isn't y. So if I take it back to the easiest case, if we had the derivative of y squared with respect to y, hopefully you guys can still see this over here, that would just be 2y. It turns out we need that component because the first step in the process is to think about differentiating our outer function. Think about this as almost a hidden inner-outer situation. We don't see an inner function, but we're assuming that y is a function of x. So we differentiate our function with respect to the variable we see. And then we're going to follow it by dy dx. So this is chain rule, but it just feels different because we're representing our outer function as y, or excuse me, our inner function is y, and kind of embedding it within a bigger problem. So let's go ahead and talk about finishing this one. If we think about our goal, to go back, our goal is to find the derivative dy dx. When we look at this particular problem, notice dy dx is involved, but we don't have dy dx equals. In the same way that when we have an explicit function, as soon as we differentiate, we get dy dx equals. But we can go ahead and solve this guy by subtracting our 2x. Okay. So subtract our 2x, subtract our 2x. And then in this case, we can go ahead and multiply through, or divide through, excuse me, by 2y. And that's going to isolate that dy dx. Now, in this case, we could also cancel the 2's. So this tells us our dy dx. Be careful we get the order right. That's going to matter for us. It's x over y. Don't lose your negative sign here. So our complete derivative is negative x over y. Now, a couple things that's different about this form. We started with a function with x and y on the same side, and we started with a y squared. We didn't solve for y equals before we started. And notice our derivative has both an x and a y, which we haven't seen before. So what I'm going to do is pause and ask you guys what questions you have, and then if we need to, we'll kind of go through our steps again. All right, so what questions do we have with this one? All right, so I don't hear anyone unmuting. So what I'm going to do is take us to another example. Just the more we do this, the more we'll get a feel for it. So let's go ahead and take a look at another implicit function. In this case, we're going to look at 3x squared plus y cubed equals y. Now, when I was trying to consider what type of examples I wanted to do today, I knew I wanted to do a circle because we're going to come back to that circle in just a moment at the end, kind of round back to it. But when I was thinking of an implicit function, I made this one up because I wanted it to work out nicely. So when I take a look at this, I don't know what it looks like until we take a look at the graph in Desmos. I haven't actually picked at that graph. So it's not a recognizable shape. I wouldn't expect you to know what this looks like, what this is. So first step of our implicit differentiation, first of all, most times the directions will say, oops, find dy dx for your implicit function. So let's just go ahead and write that function over again. I'm going to give us a little bit of space here. And we're going to differentiate both sides with respect to x. Now, one advantage on the right-hand side is that we only have one component. We have just a y. And I always say start with whatever side is easier. If you're differentiating y with respect to x, that's just dy dx. We don't have to do anything. If we're thinking about that idea of the chain rule, the derivative of y with respect to itself is 1, and then we follow with dy dx. But in this case, this is just a fancy way of writing dy dx. On the other side, we're going to think about the derivative of 3x squared with respect to x and the derivative of y cubed with respect to x. So let's start with the one where our variables match. Always going to be easier. When we take a look at this one, we're going to get, if we just differentiate power rule, 6x. Nothing else, because our variables are matching and we don't need a dx dx. Dx dx, you could write it, but it's 1, right? It's the same idea, a little bit of change in your x over the same little change. Or symbolically, those dx dx cancel, just like you would cancel an x and an x. Then on the derivative of y cubed with respect to x, first differentiate with respect to y. So if we were looking at the derivative with respect to y, we would have 3y squared. Then, anytime your variables don't match, follow it by the derivative of your inner function, or the derivative of your y with respect to x. Now, I did one thing here that we want to be careful of that I'll tell you guys not to do, and that is I dropped a parentheses. And notice you can see over here, it kind of looks like, okay, I already have a dy dx, and it's really easy to lose components. One tip that I do sometimes is just draw a straight line down the middle to divide that, and make sure I don't lose my parentheses. In other words, I should have had one right there. Now, what's different about this guy? In this particular example, we have dy dx appearing twice, not just once. And that's okay. If you have y appearing on both sides of the equation, you're going to get a dy dx every time you see the y variable appear. So you're going to get it on the left side with the 3y squared term as a multiplier, and you're going to get it on the right by itself. So before we go on to solving for dy dx, any questions here? Okay, so let's go ahead and just rewrite that same line. I can't see once I scroll onto that next page. So there's your equation. And at this point, you want to think about solving for dy dx. So keep it in the back of your mind. We're wanting to write dy dx equals, and it's going to be stuff that involves both x and y. So we need to get the dy's on the same side. And if I were doing it, I would say, hey, I need to subtract the 6x, move it to the other side, and then move the other dy over, just so there's not too much moving at once. Let's do it in 2 steps. So subtracted our 6x. And then we're going to now subtract our dy dx on the other side as well. We don't need to get this. And when we think about subtracting that, you're going to leave your first term alone, and you're just subtracting that guy out. So in other words, move it to the other side, just as if it were a z or a t. Now at this point, it looks like we haven't made things much better. We've just moved things around. But what this does is allows us to factor out the dy dx. So think about, in this case, I want you to think about a side problem over here. So if you had 3y squared t minus t. Hold on a second, guys.
Harrison,
you need a report. You're good.
What?
You're good, but you can go back and sit over there. Think about factoring out your t here.
Stop trying to get in front.
And in our first term, we know we're going to have the 3y squared. In our second term, if we factor out a t, we're going to have a 1. So if we understand this factorization, it's the same thing happening here, just looks a little bit trickier with our dy dx. So think about focusing on your dy dx. Factor it out. So I'm left with 3y squared minus 1. And then continue now that trick of bringing the other side down. Don't lose the other side of your equation. And now we're almost done. At this point, if I want to solve for dy dx, you need to remember that when you factor something out, it's a multiple, and you're multiplying those two things, kind of reverse distributing. So when we solve for dy dx, we're going to divide our negative 6x by that entire 3y squared minus 1. And that is my derivative. Notice once again, this one involves both x and y, and it's kind of hard to look at the original and predict this. So what questions do we have now? So some good questions that I would suggest thinking about is, well, if I were a student, I would say, how do I check this? We know that Desmos allows us to graph a function, an explicit function, and also graph the derivative, and then graph what we found as the derivative to make sure that those things check. It's a little bit more complicated when we're dealing with an implicit function because Desmos can't actually graph this part. Here's why. If you type in just the expression on the right side, the negative 6x over 3y squared minus 1, that's not an equation. But if you write equals a dy dx, Desmos doesn't know how to process that derivative as part of an equation. In other words, it knows how to do the derivative equals, but it doesn't know how to take this equation and plot what the derivative looks like. It's almost like it has to know the x and y value to get the derivative, not just the x value. So we have to do a little bit of workaround. At this point right now, figuring out how to check it in Desmos involves a little bit of coding. So hold on to this idea of checking. We're going to return back to it, and I'm going to show you a couple of ways that you can check. So let's take a look. Last call for questions on this one. Okay, so let's take a look at another example. So for this one, let's take a look at, let's see, make sure I'm giving you the right ones that I intended to do. Xy squared minus 5x squared equals 6. So let's think, differentiate the left, differentiate the right. And on this side, I would definitely start with the right-hand side because our derivative of a constant is going to be 0. And then this one, go ahead and start it the same way we did the other two. Let me give us a little bit of space here. But there's one thing we have to be careful of. We see the subtraction, but the subtraction separates us into two pieces. We don't want to separate the xy squared yet. We're going to talk about y. But we can also write the derivative minus the derivative of 5x squared. So again, tackle your easy pieces first. The derivative of 5x squared with respect to x is going to be 10x. Don't drop your equal 0. And then if we think about this one, this is the tricky piece. And the tricky part is we actually have a product of x and y squared, meaning we have to use product rule and implicit differentiation with our dy dx to get all the components. So I want you to think about, it's almost like you have your first function is x and your second function is y squared. Now, all the other problems we did with product rule, we had x and then maybe something like e to the x if they were sandwiched together and multiplied. Nothing like a second function that involved a y. But we can put it together and handle it okay. Remember that the product rule tells us we do the first function, which is our x, times the derivative of the second. So the derivative of the second, we have to keep on remembering that we're differentiating with respect to x everywhere. So the derivative of the second, we would first differentiate with respect to y, and then follow it by dy dx, since we're trying to differentiate with respect to x. Now, that's the first part of the product rule. This is really just f g prime. Then product rule says do your second function times the derivative of the first. The derivative of our first is just 1. So this is g f prime. Now, don't lose, in this case, your minus. A lot of times once we get good at it, I'm going to go left to right, but as you're getting acquainted, do the easiest first. So now when we look at this, we kind of have what looks to be a mess. I'm just going to highlight this part, right? Because the part beneath with the g and the f prime is just helping us understand what's going on. Now, one thing to note, gets asked quite a bit, is do we need a dy dx on the y squared times 1 term? The answer to that is no, because in the product rule, we do our second function, which is y squared. There's no dy as part of the original function. And then the derivative of f does not involve a y, so we don't get a dy dx. Now, are we finished? No. Think back to your goal. Your goal in all of this, in the back of your mind, is to write dy dx equals. So at this point, we have an equation that has a dy dx. We just need to solve for it. So here's what I want you guys to do. I want you to take a minute and clean this up. See if you can solve for your dy dx in this case. Simplify as much as you can, and then we'll go through it together. So I'm going to give you about a minute to do that, and then we'll continue. I'm just going to rewrite our problem So it's at the front. Oops. I'll give you another minute to make sure you're done with that part. All right, so let's see how we would clean them up. First thing I would note is I really don't need this times 1 part. That's just y squared. Not much I can do to clean up the minus 10x, but for my x multiplied by all of these things, this is just 3 terms multiplied together.
Or no.
We've got 2x y times dy dx. So think about when you have a string of multiplication, you can reorder those multipliers and the problem is unchanged. Now, be careful here. You don't have a multiplication here, you have an addition. So again, just kind of look everywhere to make sure you see where the multiplication is. I'm going to highlight that in purple, and where you see the additions are. Because if we're thinking about solving for dy dx, we want to get our y squared term and our 10x on the other side. Let's do that. So add 10x minus y squared. And then that leaves us with 2xy times dy dx. So if we want to isolate the dy dx, we're going to divide through by the 2xy. So notice on this one that we kind of see the same type of problem as the other. Oh, sorry guys. Okay. We don't really have a good way to check it. I don't really know what this 10x minus y squared over 2xy is really telling me unless I do some more investigation. So let's stop for just a second and see if there's any questions. Okay, so what I want to do is talk through one more, and then we're going to take a break in just a moment. And then we'll come back and take a look at the Desmos component, make sure we know how to check these things, and look at a Desmos activity. So for this next one, our function is still going to be implicit, but I'm going to change over our directions a little bit. So we're going to say, instead of just find dy dx, the derivative, let's say we have find the equation of the tangent line. To our implicit function. In this case, our implicit function is going to be x cubed plus y cubed equals 9xy at the point 2, 4. Give you a minute to read back through that. Finish writing it if you need to. And what we want to notice is what's different. When we're dealing with an explicit function, we can find the equation of tangent line at a particular point as well. But usually in those ones, they only gave us an x value. In this case, because we don't actually have a guarantee that we're looking at a function that passes the vertical line test, it's possible that for one x value, you could have 2 intersection points. We are going to pop this guy into Desmos a little bit later, but this graph actually is kind of like a loop-de-loop on this one. We'll investigate a little more, but at certain points, for example, right here, there's kind of 2 tangent lines happening. And if we have other functions, maybe like a loop that spirals upward, we might have lots of tangent lines happening. So here's what I would like for us to do. When I think about taking the derivative, I still want you to think left side, right side. unless for some reason it's easier to rearrange a little bit first. In this case, like taking the minus 9xy over isn't going to help us much. But I do want you to notice that this part is a product. So very similar to the last one, when we're differentiating the 9xy term, we're going to have to use product rule. All right, so let's do this. What I would like to do is take our break and then also give you guys a few minutes to try this one, and then we'll kind of come back, incorporate Desmos, and kind of put it all together. So I want you just do step one. Like, don't worry about the full equation of the tangent line. I want you to focus on finding your dy dx. You have to do that before we can plug in our x and y value to get our particular slope at a point. Then we'll be able to find our equation of the tangent line, and then once we do that, we're getting somewhere with Desmos. All right, so let's see, it's 239, 240. Let's come back at, let's see, let's do 12:55. That'll give us a 10-minute break if you need to kind of do anything or check in with anybody in between, and then an additional 5 minutes for you to actually find this dy dx. All right, guys, so if you have any questions, go ahead and put them in the chat box, and I'll see those. Wait just a second for those to come through. And what I'm going to do, not so many questions popping through, is I'm actually going to end our meeting. So when you come back after the break, you are just going to click the exact same link. I'll open it back up just a few minutes before 12:55, and we'll start another session. That'll allow me to upload in 2 parts as well, to divide up that recording time. All right, guys, so I will see you at 12:55. We will go over the finding dy dx, like step by step, and then proceed.